Thank you, Alexandra. Um, Good afternoon, everyone. My name's Asad Samdani, and I have with me my colleague Bart Serps. We both work at Dell Technologies in the Data-Centric Workloads and Solutions division as Oracle Solution Specialists. For the next hour or so, we'll be discussing the architectures needed for achieving high availability and techniques for optimizing Oracle data protection. So the agenda for this session is as follows. We'll start by looking at what high availability means and discuss typical availability architectures and the different methods for implementing these architectures. As database sizes grow and resources get stretched, completing backups within backup windows has become a real challenge for many customers. So we'll dive into some techniques for optimizing and accelerating database backups. As someone once said, the best data recovery strategy is one that you never have to put into practice. And that still holds true. So whilst we can optimize backup times, restoring and recovering databases can still be a stressful and time-consuming process. So we'll examine how to implement some fast database recovery techniques that can be used in many scenarios. Cyber threats are never far from the headlines, and every week we hear of a new breach. So it's critical that we understand what the threats are and take steps to protect our systems from cyber attacks. We look at how databases can be attacked and what can be done to protect data in a way that ensures isolation from the outside world. And finally, Bart's going to give a really nice, useful presentation on fast database recovery and taking snapshots or utilizing snapshots. So what do we mean by HA? So simply put, availability is the ability of a system or component to tolerate failure. There are at least two categories of availability. And I specifically want to talk about data availability and service availability because they affect database systems. Data availability stands on its own and can be provided independently. But as for service availability, it's totally dependent on data availability. You can't have service availability without the data being available. So looking at the components of data high availability, the simplest method of providing data availability is a backup. It might sound simple or silly, but yeah, that is a way of providing availability. And then beyond that, high availability for backup could be simply a replication of that backup. Whilst backups and protection of backups is important, it's the availability of primary data that supports the service availability. Consequently, high availability of primary data by means of replication or mirroring is also a basis for service high availability. Finally, both backup data and primary data can form the basis of cyber attack protection. These are the core components of data high availability. And as you can see, data HA or data high availability can stand alone. You don't need any service availability for that. However, service availability is totally dependent on data availability and can be provided in two forms: in-site service availability or cross-site service availability. And in each mode, it can be either passive or indeed continuous and active. So sometimes continuous availability is referred to as active-active, and passive could be active-passive. And we'll look at what these modes mean in more detail. So let's start by looking at what architectures can support data availability. The simplest data availability architecture is a replicated backup. This kind of protection is usually provided by means of a dedicated backup target, such as Oracle ZDLRA or a Dell Data Protection appliance. The faults tolerated are mainly, obviously the failure of your primary backup appliance. And that's very simple and is of limited use. Primary data replication can be a very useful tool if high service availability is not mandatory. What we're talking about here is replication at the storage layer, which does not require any server resources. Now, this has some benefits in that the primary data can be protected on a secondary site without incurring any additional Oracle license costs. Furthermore, providing that the network allows the server resource can be swung across to the secondary site to provide service to the users in some way. It might be limited, but it's still a possibility. And the big benefit is that you only have to license Oracle at the primary site because there are no server resources attached to the database at the secondary site. That's just one mode of operation. You can see that all you're really protecting against there is the primary storage server failure. The third architecture for data availability is to add a cyber attack protection. Now, to comply with NIST, which is the National Institute of Standards, cyber protection standards, the cyber site, protection site, has to have what's called an automated air gap, which prevents any user access. Now, whilst there may be server resources within the Cyber Vault, these are not meant to run applications and are really only present for analysis and detection of any attack. We'll have more on this later. Cyber Vaults with automated air gaps can be implemented using products such as the Oracle ZDLRA or the Dell Cyber Recovery Vault, or many other OEM suppliers of cyber recovery products. So moving on to service availability, data availability is of limited use, and really service availability is what we look to provide so that our users and customers can continue to use the systems uninterrupted or with limited interruption. Service availability architectures come in many different varieties. The first one we'll look at is passive insight HA. So that could simply be replicating from one system to another within the site. And you can extend that further to a secondary site. Now, this can be implemented using either storage replication or something like DataGuard. But what it provides you with is availability, but in a passive fashion. So if there's an interruption of, or there's a fault in the primary system, then whilst you will be able to provide service availability, there will be some kind of an interruption. The next level is non-disruptive availability, and you can usually provide that using some form of clustering, whether that be at the Oracle rack layer or at the storage layer. So this diagram just shows one possible example of a rack, a two-node rack system with a clustered mirroring array underneath. That could be two separate arrays that are mirroring between each other, synchronous mirroring, and that provides you with quite good service availability in that a number of components can fail and service will still continue. And you can enhance that further by providing replication to a remote site. Now, you might think, well, I've got enough availability, enough service availability in my primary site. I don't really need to provide service availability on the secondary site. So you might decide, well, I'm not going to have any server resources at the secondary site because I've got sufficient availability at the primary site, and I'll just swing those server resources across to the secondary storage site, thereby again saving on license costs. Again, there is no one size fits all. There are many different architectures. You can mix and match these architectures to suit your particular requirements and your availability needs. This is very similar to the previous architecture, but just taking it to the next level where you've got a cluster, but separated using what we call availability domains. So one half of the cluster would be in one cage in a data center, and another half of the cluster would be in a different cage. And that gives you slightly more availability than the previous diagram that we were looking at. And again, you can enhance that with replication to a remote site to give you additional availability. Again, this can be implemented using storage replication or data guard. Now, there are many benefits to both storage and replication and data guard replication. Both have pros and cons. There are similarities, but data guard is closely coupled and integrated with the database. DBAs are familiar with it, but storage replication can provide a one-stop shop for replicating all your data, not just database data. And also, it can replicate everything in one go, so you're not having to set up data guard replication for every database individually. So there are benefits to storage replication. But we're not necessarily talking about specific technologies here, but generally the principles that are involved in delivering high availability. And then finally, the last architecture for delivering high availability, and that's the non-disruptive in-site and cross-site HA. And this is really the holy grail. This provides for many different types of failures. You can have server failure at either site, you can have storage failure at either site, you can have entire site failure and still provide a service to your users. And again, this is normally a combination of rack clustering and storage replication at the storage layer. There have been historically architectures and white papers published by Oracle that allow the mirroring of the storage data to be done in the SM layer. I'm not entirely sure whether those are still relevant or valid, but certainly from a Dell perspective, we support stretch clustering at the storage layer, which then supports rack clustering at the database layer. So quite a useful tool in looking at where your particular environment is what's called the availability chart, which maps out the different types of architectures or different modes of or different architectures in terms of where they are for data availability and service availability. So if we look at the bottom left-hand corner, you can see that the cyber recovery data is protected, but it's not necessarily available to the users. So it's low both on the service availability and data availability scale. And then moving on to that backup backup replication, again, the data is protected, but it's not necessarily immediately available to users. So it's fairly high up on data availability, but low on service availability. And then at the top end, you've got the stretch cluster continuous availability architecture, which ranks very high in terms of data availability and service availability. So you can use this chart to map out where your existing environment is in terms of service and data HA and where you'd like to be. And that can help you determine what kind of architecture you need to deploy to achieve your availability and service availability targets. So that's enough on availability. So let's now look at optimizing backups and restore operations. So, why do we want to optimize backups? Well, there are a number of common problems that most environments have that means that backups can be, a real pain. So backups usually don't complete in time in many environments, and they can compete with batch processes, and that has a knock-on effect on the batch process and also on the backup itself. So they contend with each other, and it often means that backups don't complete in time, your batch processes don't complete in time. And then whilst backups might be completing in time, restore times sometimes, in many cases, don't satisfy the SLAs. So, looking at backup contention, normally a backup runs through RMAN in the same server as the database server. So what this means is that your application users are accessing the database, and RMAN is also pulling the same data back. So you get contention both in the server for memory resources, for compute resources, and also for the HBA resources that access the storage. Now, this can fairly easily be overcome by what we call offloading the backup. And what this requires is the ability to create or capture the state of the database at a particular point in time, and then present, and that's what we call a storage snapshot, and then present that snapshot to a backup server. And then you can run your RMAN job in the backup server, and then the contention for the memory resources, the HBA resources, and CPU resources is offloaded to the backup server. And what this means is that the backups will generally run a lot faster and have little or no effect on the application users. Now, the reason that you have to have the storage presented through a snapshot and not directly the same LUNs that the database server is using is that you can't really present, unless you have a clustered environment, you can't present the same storage to multiple servers. So thereby you have to effectively separate out the primary LUNs, create a storage snapshot, and then that separates it out from the primary storage. One of the big issues is trying to back up very large databases. Whilst in the previous slide we looked at how you can offload those backups to a backup server to reduce the contention, you can't get away from the fact that you've got to transmit all that data especially for large databases across some kind of network to your backup appliance. And usually the network is the bottleneck in these scenarios where you've got very large terabyte-sized databases. So some of the techniques that we use to try and overcome these challenges are deduplication and compression. Now, what we're talking about here is not deduplication of the source data, but effectively what we're saying is that what we try and do is see if that particular block that's being backed up or that needs to be backed up already exists in the target backup appliance. And if it already exists, then not to transmit it across the network. And if it exists, then we compress it and transmit it. So you get a double benefit there. So, in a normal scenario, if you're doing full daily backups, then a large proportion of those databases will not have changed. So a lot of those databases will already have duplicate blocks on the storage appliance. Hence, you can effectively discard those and not have to transmit those. And this can have a significant effect in improving the performance for backing up very large databases. Let's look at the mechanics of how that would work. Step one would be RMAN fetches the block from storage. It passes the block to what we call the boost agent. And this agent hashes the block and it checks with the backup appliance whether that block already exists on the storage device. If it already exists, it effectively discards it, and the backup appliance then effectively creates a link to that in the current backup. It creates a link to the deduplicated block. If the block doesn't exist, then that block is compressed and transmitted to the storage array. So that can have a significant effect. In fact, it does have a significant effect, especially if you've got a low change rate in your database. So that's one way of doing it. Another way of doing it, and we'll see why you might want to do it this way, is to create an NFS share to the database or the backup server from the protection appliance. And then the process is very similar in that the backup blocks are fetched by RMAN, passed to the boost agent. The boost agent again does a hash, checks if that block is existent, and discards it if it's not. And it writes, if it needs to write the block, it writes it to the backup share. Now, why would you want to do this? Why not just transmit it? It's effectively still being transmitted across the network, but this time it's being done via an NFS share. Now, the reason you might want to do it this way is to be able to further enhance very large database backups. So this is great, but if you're doing full backups every day, whilst you're not transmitting those full backups across the network because of the deduplication that's being deployed by the Boost agent, you are still having to read those full backups from the storage. So you can further enhance the performance of very large database backups by doing incremental backups. And then this NFS share comes into its own, because what you can do is instead of doing a full backup, you obviously still have to do the first full backup, but then you can use the block change tracking file to do incremental backups. And then again, the incremental backup goes through the backup agent, and then eventually it ends up on the NFS share. And what this means is that the full database backup plus its incremental backup is available as a backup, as a full backup on the NFS share, on which you can, Arman can operate the Arman incremental merge feature. So what this means is that you do your full backup once, and then subsequent to that, you just do incremental backups, and then deploy the incremental merge feature on the NFS share to merge the incremental merges into the main backup. This not only helps the backup time, it also means that your restore times are quicker because you're not having to merge many incremental backups into your main, into your last full backup. So just looking at fast database recovery, database backups are great, but there are times when you might want to do a really fast restore. Backup times or restore times can still be quite significant with very large databases because they do have to be fully restored from the backup. So they can take quite a lot of time. So there are alternatives that can be deployed. So there are techniques for implementing fast database recovery. Whilst optimization can be significantly reduced, restore times can still be very high, depending on the failure. So we can use storage snapshots as part of an overall backup and recovery strategy. It's important to note that snapshots or storage snapshots are not considered backups, but they should still be considered as part of an overall backup and recovery strategy because they're instrumental in providing almost instantaneous full recovery of very large databases and fast point-in-time recovery of databases to any point in time between the snapshot and the current point in time. So let's look at how you implement storage snapshots for database backups. Let's have just a review of what storage snapshot technology is. You can think of storage snapshots as point-in-time copies of storage LUNs. And these are analogous to taking a digital photograph of the LUN and its state, its data state at that point in time. You can create what are called consistency groups, which allows you to snap multiple snapshots at the identical point in time. And that's very important for database recovery. The point in time clones are space-saving clones. You're not creating an entire copy of the LUN. It's what's called a save using pointer-based technology. I'm not going to go into any great detail about this, but effectively only the before images of change blocks are stored in the snapshot. Thereby, most of the data is actually referenced back to the original LUN. So creating snapshots is an instantaneous process. It takes seconds to create a snapshot, and then you can effectively read the entire snapshot as if you've got access to the entire LUN. Now, utilizing snapshots, I'll skip over this bit. So how would you utilize snapshots to create a scenario where you can do instantaneous database recovery? Well, the first thing you would do would be to create what's called a consistency group. And what this does is to group all the various different LUNs into a single group. So if you imagine a typical 3-disk group ASM architecture, where you'd have a data disk group, a redo disk group, and FRA disk group, which would comprise of any number of LUNs. All of those LUNs would be grouped into a single consistency group. You'd put the database into backup mode, and then you would create a consistent snapshot of the entire group. And what that would do would be to create the snapshots of all the LUNs in that consistency group at the exact same point in time. And because these snapshots are instantaneous, it really doesn't matter how many LUNs there are in that consistency group, because they take such a short time to create. They can all be created at almost an instantaneous point in time. So having done that, we can then use, and then you now the backup mode is not necessarily from 12c onwards. You can restore databases without putting the database into backup mode. There's no requirement for that from Oracle 12c onwards. Prior to that, Oracle used to say that you had to put the database into backup mode. Regardless, it's almost irrelevant, simply because the snapshots take such a short time to create that if you do put the database into backup mode, it's only for a second maybe, or a couple of seconds. So it really doesn't affect performance in any meaningful way. So a couple of recovery scenarios that I can talk you through once you've created a snapshot of a consistency group. So the first recovery scenario is where you might want to restore a database, the whole database to the previous point in time, the point in time at which this snapshot was created. You might say, well, why would I want to do that? I don't want to lose any transactions. Well, what you might want to do is have a test system whereby you run some test scenarios on a test database, make some changes, or do various different things, and then you want to run a different set of tests with a different set of parameters. But you want to take the whole database back to the same point in time, and you can very easily do that by simply shutting down the instance, dismounting the ASM disk group, and then restoring the entire disk group to the original LUNs. And then you would just simply remount the ASM disk groups, start the database instance, and you're away. And that almost immediately restores the entire database to the point in time that the snapshot was taken. And this can be quite a very useful technique for test dev environments. And it can also be useful if, for instance, in a catastrophic scenario, your production database, you'd lost the redo logs. So you weren't able to roll forward the database. So you'd lost your data files and your redo logs. Then that would mean you'd have to restore the entire database to a previous point in time anyway. So rather than having to do that from a backup, you could do that from a snapshot. So multiple use cases for that. So the second scenario is where you've had some damage to some data. It could be a data file, it could be a table, and what you want to do is you don't want to lose any transactions. You want to use the snapshot that you've taken previously to restore the database to its last committed transaction. And again, it's very easy to do that using storage snapshots. So you start by shutting the database down. Clearly, the database has been damaged, so it doesn't. There's no service available at that point. You dismount the disk groups, and in this scenario, you would only restore the data disk group because the damage is only to the data itself and not the redo stream. Having done that, you would remount the disk groups, start the database instance, and then what roll forward the database. And this would normally happen automatically. The database would automatically recognize that the data files had a previous SCN, which didn't match the current SCN in the control file, and it would roll the database forward. And it would roll it forward to the last committed transaction. So you'd end up at a point very quickly whereby you'd lost no transactions and you could restore service without the loss of any data. Now, a third scenario, which I'm not going to talk about in any great detail, is a partial restore, i.e. you'd restore the disk groups as described in this diagram, but without replaying all the redo logs to the current point in time, and stop at a point in time prior to maybe perhaps when a corruption had occurred, an accidental corruption in the database, which couldn't be restored by restoring a database. So the only way you'd be able to do that would be to effectively roll back any changes that had been done since the corruption. And one way to do that would be to roll back to a point in time prior to the corruption occurring. And again, you can use exactly the same technique shown here to do that. And then finally, you just open the database. So that's details on how you'd utilize storage snapshots for aiding very fast database recovery. The final section for the presentation part anyway is cyber protection. So just a very quick dive into what cyber recovery is and how you'd mitigate against some of the threats. There's a broad spectrum of threats, from crime to insider threats to espionage, terrorism and warfare. Not every organization is susceptible to these, but most large organizations will be susceptible to some of these at some point in time. Make no mistake, virtually every organization will be hit by some kind of an event, whether that be insider or terrorism or crime or whatever at some point in time. So every customer has to be aware of what the threats are and how you can protect against them. In terms of databases, generally people think, oh, well, users don't access the database, so we're immune, the database is immune to cyber threats, but that's not actually the case. There are a number of database attack techniques that bad actors can deploy. Easiest one being gaining unauthorized access, spying on network traffic, SQL injection. So if your application hasn't been designed correctly, then they can use an application against you to inject SQL into the database, exploiting unpatched systems, and so on and so forth. So databases are very much susceptible to various different attack techniques. Now, there are a number of key requirements for cyber recovery, and they are very different to database backup. Don't think of your backup as being the same as cyber recovery. It is very different, and they have different requirements. And these requirements primarily are an isolated vault. Your cyber protected data has to be isolated in a cyber recovery vault. It has to have the characteristic of immutability, in that it can't be changed. Once it's reached the cyber recovery vault or been updated with the latest data, it has to be immutable. It can't be changed. You have to have some form of intelligence to be able to analyze the data for ongoing threats. So what often happens is that a threat will happen or an attack will happen, but you will not become aware of that threat until a later point in time. What you can do within the cyber vault is look for common threats, and that's what the intelligence part of the requirement satisfies. And then obviously you have to be able to recover from the cyber recovery vault. This is how most cyber recovery vaults operate. They have an automated air gap, and what that does is effectively satisfies the isolation requirement of cyber recovery. So users can't access the cyber recovery vault in any way. Clearly, there is a small window of opportunity when there's a sync that happens between the data center and the Cyber Recovery Vault, but it tends to be a very small window of operation, and only certain kinds of data and actions can be performed over that link whilst that synchronization is happening. Once it's reached the Cyber Recovery Vault, a copy is taken immediately, and that copy is locked, and that's the immutability aspect and requirement of Cyber Recovery Vault. And then the fourth characteristic is the ability to analyze the data, and then obviously you'd run the analysis on the non-immutable copy, because when you're analyzing data, you might have to open the database, which requires some parts of the database to be changed. And that's the purpose of taking that copy and locking the copy, because once you've locked it, you can't access it in any way. And then you've got monitoring and reporting. And then finally, the final aspect is the recoverability portion of cyber recovery. So all of those requirements need to be satisfied in any cyber recovery solution. This is just one possible cyber recovery solution from Dell EMC, which satisfies all the requirements that we talked about there. But there are other cyber recovery solutions out there. If you want to talk to us about cyber recovery, by all means, you can go to the link there, or call anybody at Dell Technologies, and we'll be happy to talk to you about cyber recovery or any of the technologies we've talked about today. So that's all I've got to say from a presentation point of view. I'm going to hand over to Bart now, who's going to do a live demonstration of snapshotting technologies and in conjunction with databases. So I'll stop sharing and I'll hand over to Bart.
Thanks, Asad. So yeah, let's quickly move into it. Yep, I'm going to share my screen. I'm going to first quickly go again over a couple of things regarding snapshots. So there, as Asad already discussed, there's multiple purposes for snapshots. Mainly, I think there is two categories. One is to take a snapshot of a database and use it elsewhere for something else, like test and dev, maybe ETL loading, these kind of stuff. And the other one is to have a snapshot available in case something bad happens you want to restore. And I want to do a quick demo of both of these scenarios. I'm going to quickly skip over because Asad already showed a couple of things, and this is animated. So I'll quickly show what the demo environment looks like. So we have a source database host with Oracle 19, Oracle ASM, and it's using a set of LUNs. And in this case, the underlying storage is PowerMax, one of our storage arrays, the high-end platform, which is very capable, but also a bit there's a lot of command line options and all these things. But I'll show you a little bit how that works. But so this box typically, you have a set of LUNs that takes its storage from a storage pool, so like one large pool of disk capacity. And it's all virtual provisioned, so the original data uses pointers to chunks of storage that are allocated, right? So at some point, I'm going to make a snapshot. So the only thing I have to do at this point is to copy that metadata in memory, like where are my actual blocks on disk. So if I do that, it would look like this. So this is my snapshot, right? And at the point that I make the snapshot, which is very fast, it would be a fraction of a second. At that point, all my pointers from my snapshot are pointing to the same offsets in my storage pool, right? So it doesn't take any capacity until my original database modifies data or I modify something on the snapshot. And I can have multiple of these snapshots. And at some point, the locations to which they point, in terms of blocks will be slightly different as data starts being modified and all that. At this point, my snap 1, 2, and 3 are still living inside of my storage box. It's not yet visible outside. I can't do anything with it. Well, maybe restore, but I don't have a purpose yet. So what I need to do is to set up a copy host with some storage. And at the point that I do this, the storage will be empty. And now I can link it. This is the concept in PowerMax. I link it to a snapshot. And now I can see the data on the copy host that lives in snap 1. And I can relink it to snap 2. And so I can change the, the switch, if you will, to different versions of snapshots. So I can look at different, points in time of my database replication. So this is how it works. I just wanted to give you a little bit of background of what I am doing to make it a little bit more sense. So here are the steps we need to do to copy database. I will not go over the steps, but fundamentally, if there is an older copy running, you have to stop it and unmount it. Then you do a couple of steps for managing metadata, create a snapshot, and then you import and mount or recover the database again from a snapshot, right? So that's what we are going to do. So on the test environment then, and I'll show you quickly what it looks like. So, and these are both virtual machines. The production, we have a production virtual machine with a database, and we have a recovery virtual machine on which we will do the snapshots, which we will do first, and then later we'll also do the, we'll basically destroy the production database and see if we can recover it. Okay, so that's what we will attempt. So quickly, this is my production virtual machine. What does it look like? Well, at this point, I have a container database with 2 pluggable databases on top of ASM. If we look at a disk environment, you will see a boot disk. You will see this is the disk for Oracle Homes, and here we have the ASM disks for various stuff. If I do an LSCSI, you will see that the first 2 are virtual disks. But these ones are actually raw disk mappings in VMware. Why? Because I need to have access to the raw disk and not to a virtualized a chunk of that, because that wouldn't work, directly with snapshots. So this is what it looks like. We can go log in as a grid user and look at it from within Oracle ASM, and then this is what you see. And by the way, I'm not using this yet. But here we have my data disk, which is 64 gigs. I'm not using a lot. This is, the database is actually very small. I have my FRA for my redo logs, and I have 2 pluggable databases, and each PDB sits on its own dedicated ASM disk group and volume. And then finally, we have the redo logs. Okay, so it's pretty straightforward. Going into the database, you can look at the data files. So this is what we have. If you're familiar with pluggable database, you'll recognize this. We have the container, pluggable database 1, pluggable database 2, redo logs, temp files. Pretty basic. So we are going to look at the target server. So this is my recovery VM, and here, if I look at my environment, what is running? Well, the only thing is the platform. So we have. Where do I have this? Here's Oracle ASM. As you can see, and nothing else. I have no database running. There is some disk space allocated here, but it's all, this is a tool I wrote to manage ASM disk, and you see all these disks are blank. There is nothing on it, completely empty, right? So like I said, the first thing we have to do is make a snapshot, and the second thing we have to do is to link these set of volumes to that snapshot. And to make life a little bit easier, I created a small script to do that. So in order to create a snapshot, I will do something like this, snap vx, create, because if I do a list, you will see it shows up as empty, no snapshot was found. We could, by the way, took a look quickly at the storage. This is my storage environment. So we have 3 of these PowerMax boxes, but we're only using this one with serial 615. We look at storage groups, and these are the storage groups that Asad was talking about, like how I group my volumes together. And here you see a group called Oracle_CDB, and this is the one I am using. And you will see in there is another storage group called Oracle_CDB_data. We have a redo, and we have PDB 1 and 2. FRA is separate, as you see here, and this is the linked copy. And the linked copy has an equal amount of devices as in the other one, because if you want to copy this group to the other one, then you have to have the same capacity, obviously, right? So why do I have this parent-child level? Well, because I'm also at some point willing to restore only the data disk group or a combination of these things. So that's why you have this multi-level setup. So no snapshot is found. So what if I do something like this, snapshot create? And my snapshot is already done. Did you see how quick that went? I created a snapshot. And if I now do list, you will see that we have one generation of snapshots, and it uses these 4 volumes. And if I look at my disks, they are still blank because I didn't link those volumes yet to that snapshot. So let's do that. Snap VX link. And now if I do something like this, ASM, now you see the signature has changed on these disks. And I can go to grid. Look at my disks, and now you will see that my disks are showing up as members, and I can actually mount it at this point and look at my files. However, it would be a bit of a challenge to use this as a full database because I didn't do anything with hot backup mode yet. I'm just creating the skeleton to do further steps, okay? So, but at this point we have a kind of like a snapshot and we have it mounted on the copy host. So now we are going to do the whole cycle of copying the database with a snapshot, recovering and all that. So for that, I have a kind of like a small script, which is maybe 150 lines in a shell script. It's not that much, it's just a bunch of commands. And if I do db snap all, I'm going through the whole cycle, and watch carefully how quick some of these steps are going, and there are timestamps built in as well. So I do, and by the way, before I forget, I have Swingbench running on that primary database, on Pluggable Database 1, just to generate a little bit of load, so you can understand that while this is, actually processing data, we are making the snapshot, and without too much production performance impact. You will sometimes see a little bit of a dip here while we are doing the hot backup mode and stuff, but actually nothing to worry about. So let's do it. db snap all. So it's going to stop any existing database. It doesn't exist, so it's complaining a bit about missing disk groups. That only happens the first time, by the way. And now I'm going to do this whole hot backup mode thing. Boom, you see a little bit of a CPU spike. Not sure if I see, well, I don't even see anything with the transactions, so it's looking good. And here it's already done. So if you look at this, so here's the timestamp when we started, 41 minutes, 38 seconds, and the whole cycle was already done here, 41 minutes, 57 seconds. So that's the whole cycle, going into hot backup mode, creating the control files, some archive logs, doing the snapshots, going out of hot backup mode. So this is the total period for which my production database could be impacted even a little bit, right? Now I'm doing all the stuff on the client side, like picking up some configuration files like init.ora and a control file and all of these things. And here I'm going to start a recovery. So if you're familiar with Armen, then you'll probably recognize this. Media recovery complete. It's going to create a few temp files and stuff like that. Usually takes a few seconds, and boom, we are done. And we have this demo database ready, and it's also renamed. And because I don't like to have the same the same SID, because that might cause confusion if you log into it. At some point you don't know anymore, am I on production or on my snapshot? So I always make sure that it's renamed. Logging into the database. So here we have the demo database. I can list my data files and it looks very similar. I think the only thing that changed a little bit is the control file, because we created the new one, and the rest is all similar. LSPDB. So here are my 2 pluggable databases. So this is how I basically use a snapshot to use for repurposing test and dev, these kind of things. You could go further and also rename the disk groups and the path to all these files. That's possible. I just didn't do it here. Anyway, so at some point I want to do a refresh, so I could do that as well. I can say db snap all and let that go. And this will probably take a minute or so, not too much. Again, here is the timestamp where we start the hot backup. Do we see some impact? Yep, we see a little bit of CPU increase for a second or two maybe. And here we are already done with the snapshot. Backup mode is ended. So it's very quick. And as said, this database is not so big. It's just maybe 10 gigabytes. But if you make a very large database, this whole process doesn't take much longer. It's still half a minute or so, and the whole process is complete. So second thing, what I wanted to show, let's see how we are doing for time. I think we are pretty good. So while this is completing, and it will probably finish in a few seconds and give us a refreshed copy database. The second thing is, how do I protect my database against total failure and stuff like that? So going back here, you will see that I have this snapshot called Oracle CDB Snap, and I have one generation, which is basically one copy. But now I want to do roughly the same thing, but for backup. So I want to have a snapshot in my storage system, which I can use if my primary database is completely corrupted. And mind you, I'm going to do this without hot backup mode, because I never know when the corruption happens, so I should be able to avoid it. So I can do something like snap x backup, and backup is nothing else than creating another snapshot with a different name. So that's all it is. If we now do a list, and you will see, make this a little bit bigger if possible. You will see now I have a snapshot with the Oracle backup name, and the other one still exists, but I'm not going to use this for now. So I have a backup, right? My database is still running. I'm going to log in. I'm going to do a shutdown abort. Going to kill it. Okay, my transactions are stopping, and I'll end this because it's giving me some headaches anyway. I still have my disks, so I am going to completely destroy my disk groups. I'm going to drop all my data disk groups here. Boom, there we go. And now you see it's all showing up as former, so my database is basically toast now. I can do nothing to make this work again, except maybe restoring a backup or something. Even my redos are destroyed. I'm leaving my FRA, but I could throw that away as well if I wanted to. Total failure. All my data is gone. Oh shit! What do I do now? Okay, well, just going to do a restore, right? So snap vx restore. This is just a wrapper script for some underlying commands to the storage array. But this is what I'm going to do: snap vx restore. And I just created I just need to make sure, because I need to be sure that my disk groups are unmounted. Otherwise, this will be corrupted within a second again. So, but it is unmounted. So I say yes. I say yes for the PDB1. I say yes for PDB2. I think, by the way, I should have done. I think I should have done that one for everything. So snap restore. Need to look up the actual subcommands, but here they are. Snap vx, rterm, snap vx, rest all. This is what I actually wanted. Yes. And here you see that full Oracle CDB group again, and I'm going to restore it. Just have to clean up a little bit. If I do it like this, ls disks, now they're all coming back as member, right? All my disks are now basically restored from my snapshot. I'm going to mount everything. Takes a few seconds. List my disk groups, and you will see everything is back online again. So let's see if we can start a database. Oops. Oh, I was already. No, I need to connect again, of course. Start up. See if this works. Database mounted. database opened, there's PDB, and we see that my pluggable database are also available again. So I could actually start up Swingbench, and before you know it, and I have to load my correct benchmark. One, open, and I'm starting my application again. Boom, back in business, and the business is happy again. So the only thing I have to do now is to clean up a little bit. So how this works is this will actually update my data disks in the background while my database is already running and recovering. So while that is done, I can do this, this terminate again, clean it up a little bit, and now you see the backup is still here, but I have finished with the snapshot restore, and my database is back in business. Now, let's say I have a software bug that was creating this corruption, and 5 seconds later, boom, I have this corruption again, and my database is completely frozen and toasted again, right? I could do this whole cycle again. I still have this backup, which is frozen. It's like a read-only copy. I can restore it again to production and, you know, try to fix my issue. I can do this as many times as I like until I fixed my bug or whatever the problem was. So that's how this works. And we're a little bit out of time. I could show you the partial restore where we do, only a restore of data and then the 2 PDBs, and then use the existing redo logs to the recovery until the last transaction number. But we're a little bit out of time. So I just want to end it here. I think you have a good idea of how this works, how fast it is, and how relatively easy it is to work with once you have the setup in place. If that makes sense. So with that, I'm going to stop sharing, and let's see if we have any questions and answers.